So on to the final question for paper 1, and the question says that the acceleration of a drone moving in a straight line during a particular interval can be modelled by this function here, where t is in time is in seconds. So this is an acceleration function. Now they give us this and they said if the speed of the drone is 1.4 meters per second after 1 second, what's the speed of the drone after 5 seconds? But of course, you don't have a function for speed, you have a function for acceleration. So here's a general rule of thumb for you that you can remember. When we have an equation or a function in distance and time, if we differentiate that distance time function, the first derivative is the change of distance with time, which effectively is speed, or now your first derivative is now a function for velocity. If you differentiate the velocity function, you're now looking for the change in velocity, which of course means acceleration. So this is the order that we'll remember things in. If we have a distance time function, we know we can differentiate that, and our derivative is a velocity function. If we differentiate our velocity function, we now have an acceleration function. This is something you should remember. We're given the acceleration function. We want the speed function. So we're here and we have to go backwards. What's the reverse process to differentiating? Well, that's integrating. So we actually have to integrate this function here to bring us from here backwards up to a velocity function. So effectively I have the integral of 0.2 t plus 0.3 t to the half. We're not going to write the square root symbol, we're going to put it to the power of a half, right? And that's with respect to t. So let's integrate this. So we increase the power by 1 on t and we divide by that new power. So t is going up to t squared and now it's going to be over 2. So what about the next one? That's 0.3 t. Now if we increase a half by 1, we get 1.5 or 3 over 2. But we also have to divide by that new power. Also, since we have no limits, we have to tag on a constant here for that. Now let's tidy up this a small bit. There's a couple of things we can do. I suppose divide 2 into the 0.2 and that gives us 0.1 t squared. I can't do much more with that. Now, when we're dividing by a fraction, you may have remembered from primary school even, or the start of your junior cert maths life, when you're dividing by a fraction, we say flip it upside down and multiply. So if we're dividing by 3 over 2, we can flip upside down and multiply by 2 over 3. What will that look like? Well, it will be 2 over 3 times 0.3 t to 3 over 2, and of course still c I can't do anything with. So now a small bit of tidying up here, and that's going to give us 0.1 t squared, oops, out the front. Now 2 over 3, well the 3 into this makes that 0.1, so effectively this makes this thing here 0.2 t to the 3 over 2, and we have a plus c. Okay, so this is our integral of a over t, but this is a velocity function, so we can actually call this v of t function if you like. Now one thing that we don't want is this plus c, because where does it go here? And that's why they gave us this information. Well, they said after 1.4, after 1 second, its a speed is this. So that means that if we replace t by 1, we should get an answer of 1.4. So essentially I can make this equation 1.4 equals to 0.1 t, which is now going to be 1, squared, plus 0.2, and now t is going to be 1 to the 3 over 2 plus c. Now we have one equation, one variable, we can solve that for c. It should be fairly easy. 1.4, well 1 squared is not going to do anything to the 0.1. Similarly 1, if you cube it and then square root it, whatever you want to do, or 1 to the power of 3 over 2, so it's going to be 1 plus 0.2 and a plus c. So we can see that when we bring this guy and this guy together, it's 0.3. Bring him over, that makes this 1.4 minus that 0.3, make them 1.1. So we can see that 1.1 is actually c. Now, so we actually have our velocity function then without a c. It is 0.1 t squared plus 0.2 t to the 3 over 2, and now plus c, which is 1.1. Now what do they want us to know? They want to know what's the speed after 5 seconds. Well, we'll just simply get v of 5. That's going to be 0.15 squared plus 0.25 to the 3 over 2 plus 1.1. Now let us put all that into our calculator, and we will get 0.1, that's right, bracket 5 bracket squared plus 0.2 bracket 5 to the power of 3 over 2, and then down here plus 1.1. So it says correct to 1 decimal place, so I got 5.83. So therefore my speed is equal to 5.8, and let's not forget the units, meters per second. So that's the first part done. Now the next part says find the average speed over the interval between 1 and 9, where t is bigger than or equal to 1 and less than or equal to 9. So essentially, if you like, you have some velocity function where the velocity is maybe going all over the place. And what we're going to do is we're going to pick the values between our limits based between 1 and 9. And we're going to look in this section here and see what's that happy average or medium in there. So to do this, actually, when you see average speed, it is looking for an average value of a function. You may know now at this stage that when we see the word average value, we must integrate the function. And when we integrate it between those limits, we divide by the distance between them. And often you see a formula like this, 1 over, say, b minus a times the integral of f of x, of course with respect to dx, something like that. But essentially all that is you integrate the function between your limits, a and b, and then you literally divide by the difference between the two. So for us, we're going to integrate this between 1 and 9. And when we get that answer, we're going to divide it by 8 to give us our final answer. So let's integrate this thing here now. So integration there, symbol, and we're integrating between 1 and 9. So we have limits, and this is what we're integrating. So I'm very particular on the notation for integration because it's often written very badly where symbols are continued on when they don't need to be. So let's take our time doing this, and we'll do it nice and slowly. So first off, when we're going to integrate, we're going to drop the integration summation symbol here. So I'm going to draw a straight line just to remind us of our limits. Now increasing the power by 1 and dividing by the new power, that goes to t cubed over 3 plus, and now it's 0.2. T now goes to the 5 over 2, up 1 from that, divided by that 5 over 2, and of course 1.1 tags on a t. We don't need a plus c here, just in case that's something you wonder about. Why do we not need a plus c? Well, because we have limits. We have a definite integral. If we had an indefinite integral, we'd have a constant to tag on. No need for that here because we have definite limits. Okie doke, so now when we actually do this, we have to take our top limit in here first and subtract using our bottom limit. So I'll use square brackets for this. Now let's put in the top limit, 0.19 cubed, and then it's over 3, plus 0.2, this time 9 is to the power of 5 over 2, and it's divided by 5 over 2. And yeah, I could have flipped that upside down and multiplied, but I'll just leave it in for now. Plus 1.1, and t is replaced, of course, by 9. So that's our top limit. We subtract from that our bottom limit. So that's 0.1, and t is now 1 for our bottom limit, cubed over 3 plus 0.2, t is 1, to the 5 over 2 over 5 over 2 plus 1.1 with a 1. This stuff here, the ones aren't going to do anything because 1 to the power of anything is going to be 1. So we can actually, this is a fairly easy side to do. This side a little bit more tricky, but let's see if we can put this into our calculator and see what we get. So we'll try and do it all in the one go and see does it work or not. So 0.1 and 9, and that is cubed and 3. And then plus, and that's 0.2 bracket 9, and that power is a 5 over 2. But of course all this thing should be over another 5 over 2. A bit messy on the calculator now, but we'll chance it. 0.1 times 9 equals, so I got like 1341 over 25. Minus Now, as I said, no point even putting the ones and the powers in here, it's not going to do anything. So I get 0.1, and that's over 3, plus 0.2, and that's over 5 over 2, and then that's a plus 1.1 equals 91 over 75 I get for that. So 91 over 75, so when I get 1341 over my 25 minus whatever I got the last time, and that gives me a 52.46. 0.426, but let's remember that this is the integral, but to get the average value, right, I want to divide that by the distance between these two functions. And I said this is the type of formula you may remember. The average value, it says that we must do 52.426 divided by what's, well, 9 minus 1 is going to be 8. I'll put it in red so you see that's what the difference is for average value. So divide that by 8, and that gives me 6.553 repeating. So 6.553, and it wants it to one decimal place, so that means that we have 6.6 meters per second, and that's our answer to that second part. Okay, so I hope that was slow enough and explained well enough for you. Now on to part B, and in part B it says a chemical process is controlled by the release of some catalyst into a chamber, and the volume of the catalyst released is given by this, so where V is volume and T is time. So how is the volume changing with respect to time, or what volume is something going in there at? Well, volume is in litres and T is times in hours, so litres per hour, how quick is this thing coming out of the pipe or whatever, and it's given by this expression here, 2e to the t plus 2e to the minus t. It says, well then, what rate is the process happening initially? Now when you see the word initially, especially in functions and differential calculus, initially essentially means time is equal to 0. Just as it's about to happen at the very start, well, its time starts at 0 here for us. So there is a rate of change at 0 here for this function. So what is that? Well, this is the rate of change function, so let's replace t by 0. So for us, when t is 0, what's dv dt? Well, it's 2e to the 0 plus 2e to the minus 0. So minus 0 obviously is just 0. Anything to the power of 0 is just 1. That's 2 times 1 plus 2 times 1 again, which is equal to 4. So the answer is actually 4. 4 what? Well, it's litres per hour. So that's literally the answer to the first part. Is pretty easy. Now, the next part says find an expression for the volume, right? Again, this isn't too bad. We have an expression for the... We have an expression for the change in volume. So if we're looking for an expression for the volume, we are just looking for the volume at any time t. And you can actually see that we have dv dt. So if we have the rate of change of volume, we must have to go backwards to find the function for just v. So if I had a vt function, that means I would have had volume in terms of t's, yeah, or the volume at any time t. I must have differentiated this, and if I'm differentiating v with respect to t, I would have had dv dt. So I want to go backwards. So if I would have differentiated to get to here, I must integrate this to get backwards. So integrating this thing here. So integration of 2e to the t plus 2e to the minus t, and that of course is with respect to dt. So when we do this, what happens if you integrate e to the x? Well, let's remind ourselves of that. Well, the integral of e to the x is actually e to the x, nothing changes. But if there was a constant or a coefficient with the x, e to the 2x, what do you do? Well, again, it doesn't actually change, but you do have to now divide by the derivative of the stuff up here. What's the derivative of 2x? It's 2. If you're differentiating, you would multiply by the derivative, so it's actually the reverse process. So again, to integrate this, it goes to e to the 2x over 2, or divided by that derivative. Why does this not change? Well, it's the same process. Its derivative, its the integral of e to the x is e to the x, but now divided by the coefficient of x here, which is 1. And of course, if you divide it by 1, nothing's going to happen. So for us here, to integrate 2e to the t, well, it's going to be 2e to the t again, and we're going to divide by the derivative of what's with t, which of course is 1, so there's no point in changing anything there. And also we're going to look at this one. This is going to be 2 and then e to the minus t again, but now we do have something that's going on. The coefficient with t is not 1, it's minus 1, so we have to divide by minus 1. Yeah. Let's not forget we have no limits, so we must tack on a c. And of course, dividing by a minus is the same as multiplying by a minus, so really it still is 2e to the t out the front, but now the dividing by minus makes this whole thing minus 2e to the minus t plus a c. Now, this is not finished, and it may seem unfair to you that it's not finished, but they do want a specific function for volume. We can't have a volume with an arbitrary constant in here. We have to know what that constant is. So, can I call it common sense? I don't know. It's hard maths, isn't it? But if you want to know what you have to do here, well, it's a volume function. Before there's anything before this process happens, initially, if you like, what's the volume of this thing? Well, before we start pouring anything into this vessel, the volume is going to be 0. So we know at time 0, the volume has to be 0. We have a function for volume here. We know if we replace t by 0, this whole thing should be equal to 0. So that's 2 e to the 0 minus 2 e to the minus 0 plus c. That means at time 0, my volume must be 0. This is 2, because e to the 0 is 1. E to 0, this is minus 2, plus c is equal to 0. 2 minus 2 is gone. So what have we got for c? Yeah, well, c is actually only equal to 0, it turns out. So yeah, it may seem a little bit unfair to have to go that far. So, but we can definitely drop our constant now because we know our constant will be 0 for this. So actually, v of t is just simply equal to 2e to the t minus 2e to the minus t. And that's your answer for that part. And the next part, we're told that if the volume is 3 litres after k amount of hours, show that 3e to the k equals 2e to the 2k minus 2. So we have our function for volume. It's 2e to the t minus 2e to the t, but they want to change t with k, right? So if we change t with a k, so the volume at some k hours, that's going to be 2e to the k minus 2e to the minus k. And we're told at k amount of hours, it's equal to 3 from the very first part. But then it says, given this piece of information, show that it should look like this. Well, we don't have this is the function we have. We look at the left hand side, something similar to here. The right side is just a 3. We need this 3e to the k, so maybe if we multiply across the function by e to the k, like so. What's that going to give us? Well, let's multiply the 3 here first to get it in the same order as this. That gives us the 3e to the k. Now equals to, so the right hand side, 2e to the k times e to the k minus 2e to the minus k times e to the k. So I've multiplied everything by e to the k. I have my 3e to the k here on the left hand side. Now, e to the k times e to the k, what happens to these pairs? Are they multiplied or added? Well, they're added like this. So now I have 2e and I have 2 k's, so it's 2k. Again, these pairs are added, so minus 2, e to the k and e to the minus k ends up being e to the 0, k if you like, or just e to the 0. And of course, e to the 0 just goes to be 1. So yeah, I actually do get 3e to the k, 2e to the 2k minus my 2. And then it says in the next part, find the value of k then, given that information, right? Hence, find the value of k. So, we're left with this equation here. Okay, so what can we do to this? Well, if we look at this for a minute, there is a substitution type questions you get that are similar to this, but I'll do it out for you. you're definitely at the higher end of reasoning here, I think, and figuring out. If you've studied well enough, you probably may spot it straight away. But I'll show you what to do. It's kind of like an equation that looks like this, if you remember it. You had something like this: 2 to the 2x plus 3 to the x, say, plus, or maybe minus, sorry, 2 to the x minus 3 equals 0. So you get something like that, and it looks real odd. Well, you can actually call this 2 to the x times 2 to the x, or something like so here, and then you have 2 to the 2x. And then you can actually do a u substitution here, or a y substitution if you like, for something here, and you can say, like, let y equal 2 to the x, and then you have a quadratic equation, you know, something like that, which gives you a y squared and a minus y and a minus 3. So it's similar to, like, they're like question 1 on paper 1 normally, or question 1, 2 or 3 an algebra question. You have something similar here. So let me rearrange this here for a second. So to make it a quadratic, of course, to solve quadratics must bring all to the one side and make it equal to 0. We usually keep the highest degree power as a positive because it makes it easier for us. So look at this one. This is going to be the highest power we have is 2k. So let's start with this here. So we're essentially bringing this guy over. So we'll have our 2 e to the 2k. We'll have our now minus 3 e to the k. And we'll still have our minus 2 over here equals to 0. Okay, so when we look at this here, we can say, alright, what's the substitution? Well, we're going to write this like this: 2 times e to the k times e to the k, because that's e to the k, that's e to the 2k, minus 3 e to the k minus 2 equals to 0. Okay, so when we're down to here now, we will look at ourselves and say, alright, what kind of substitution can we do here? Well, we can let, say, x equals to e to the k. So this is a substitution we must kind of mark out. So this is what we have. So if that's true, and we're replacing all our e to the k's by x, we get 2x squared, yeah, minus 3x, because e to the k is going to x, minus 2 equals to 0. Now we can solve this as a pretty easy quadratic for us to solve. Let's see. So it looks to be minus 2 and a plus 1. Yeah. So that means then 2x is either equal to minus 1 or x is equal to 2. Yeah, x equal to minus a half or 2. Now, if this is true, right, then we have two substitutions to go back in here. So we figured out x can be minus a half or x can be 2 for this substitution. So would minus a half work? Could I let minus a half equal to e to the k and find something there? Well, no, I can't. There's nothing you can put e to the power of to give it a negative answer. And if you like, even if you're into your calculator, you want to bring this k down, you will be getting the natural log, say, of both sides. But of course we can't get the natural log of a negative number, so minus a half is actually no good to us. What about 2? Can we let 2 equals to e to the k and figure out k? Well, we can. We can actually say the ln of both sides. That gives us the ln of 2 is equal to the ln of e to the k. They cancel, leaving us ln of 2 is equal to k. Now we need our answer to the nearest minute, so while every part of me wants to leave that as ln of 2, I actually have to go ahead and solve this, right? So natural log of 2, what do we get? We get 0.693, and let's go 147, because we have to go to the nearest minute, is equal to k. K is equal to this, but what's k? Well, k represents hours. So 0.693 hours, how many minutes is that? We'll just multiply it by 60. We get 0.69, we get 41.58 hours is equal to k, or sorry, 41.58 minutes. And it says corrected at the nearest minute, so that's going to be 42 minutes then when you do that. Yeah, so I hope all that made sense. Definitely this is a whole other section of algebra that you kind of need to know as a substitution thing. So if you're confused in this part, maybe look up these substitutions. It'll be in the logs section of your book if you want to look it up there, solving substitution style equations for logs, and see if you can find it from there. Yeah, this one is a bit of a strange one, and I had to kind of read it a couple of times to see what they're actually asking me here. Still not really happy with it, but however, we'll go on. I've looked at the marking scheme for this particularly because personally I think it's asked in a kind of an overly confusing way. but however we'll answer it. It says this stuff here are the first three terms of an infinite series for e to the x, where the absolute value of x is less than 1. So for like an infinite series, I mean, you're going to approximate to some number if your ratio is actually smaller than 1 of your x. So I mean, that's kind of something that they talk about for infinite series, in case you're wondering why here. But it's like an overly easy question when you look at the marking scheme, but I think the way it's asked doesn't make sense. That's my personal opinion, however. So it says if this is an approximation here for an infinite series for e to the x, what about an expression for e to the minus x? Well, you're just literally replacing your x by minus x. So for this one, we're going to have 1 plus, and now we have a minus x, and now we have a plus, and we have a minus x squared over 2, which of course is 1 minus x. Minus x squared is a regular plus x squared over 2. Okay? Given this information here, which essentially they're kind of saying e to the x is equal to this stuff and e to the minus x is equal to that stuff. So if that's true, what about, can we simplify this stuff a bit? Can you write this in terms of x a bit easier? So find an expression for, write this stuff here just in terms of x and see what we can get. So we're dropping the e's now because we're using these instead. So 2 times e to the x. So what's e to the x? That's 2 times 1 plus x squared over 2. Now plus e to the minus x stuff plus another 1 minus an x this time, and plus an x squared over 2. So inside we have a 1 and a 1, so plus x and minus x cancels, and we're left with 2. Now we have 1 plus 1 being 2. X squared and x squared over 2. Well, that's a half of x squared and half another x squared. That's just a regular x squared then, yeah? So then when we do that, we have 2 times 2, which is 4, plus 2 times x squared, which is like 2x squared. That's actually it for that part. I really, it's a question I struggled with, and I wouldn't think I would, but there you go. Now on to the last part. It says use our answer from the previous part there, find an approximation for the volume of the catalyst released into the chamber after the ln of 2 hours, which was the K value we just got. So using our approximation from the last part, they talk about using this part. And why would they say that? Well, they have the volume function here, the rate of change in volume, and the rate of change in volume was given to us at the start of this. But of course, if you look at this, yeah, we can factor out our 2, and we can say that's the same as 2 e to the t plus e to the minus t. And now if we look, it's the same just with x's here. So if we can approximate for our x's to go to something like this with our t's here, right? Or sorry, that's an x squared. We can replace the x by t, which is what essentially we've done. We can say this can approximate to the same thing where we've replaced x by the t or t by x or vice versa. So what am I saying? Well, instead of writing dv dt like this, we can approximate dv dt to be this stuff. 4 plus 2 now and t to be squared. So again, we were given this in the start of the question, the very first part of the question. Now we're down to here. We were told in the last part, well, you can actually approximate 2 e to the x plus e to the minus x to be 4 plus 2x squared. Well, if we can do that with the x's, we can do the same with the t's. We can just replace that x by t. And now what do we want to actually figure out from that? Well, from that then we want to figure out what's the total volume after this many hours have passed. So between 0 and ln of 2 hours, we have to integrate this thing to add it all up. 2t squared, and of course integrate with respect to a dt. So why don't we go ahead and integrate this, nothing major here. So we keep our limits like so, but we're going to integrate. So integrate with respect to t, 4 is going to be 4t. This is going to be now 2t is going to go up to 3, and we're going to divide by that 3. So we're integrating between those two limits. That means we're putting ln of 2 in first. So we have 4 times the ln of 2 plus 2 times the ln of 2 to be cubed over 3 minus, now all that stuff is replaced with zeros. Now if we replace all these terms that have variables attached on with zeros, we're going to leave us with a 0. So this whole term is now gone, and we're just left with this stuff here. So what does that stuff actually come out to be? Well, when you do all that, you get, I'll do it on the calculator here. So we get 4 times the natural log of 2 and plus 2 times the natural log of 2, but that is now cubed, And I'll make sure the cubed is only affecting the natural log of 2, put an extra bracket there and here, and that's actually over 3. So we do all that, we get our 2.9946, and of course this is going to be a volume, and what was our volume in at the very start? It was litres. So we're going to just approximate. 2.99 is close enough to say our volume after that then is going to be essentially approximately just a 3 litres. And that's it. So what did I do? Well, we had to use our answer from the last part. So user answer for the last part, we had a function for volume change here, which was 2e to the t plus 2e to the minus t. We could take a 2 out there and make it look like this. It now looked like the thing we did in the last part, except t's had x's, where that's the only thing it differed by. And we approximated in the last question that 2 times this stuff went to this. So similarly, 2 times this stuff can go to this again, except we replace t's by x's. And now we could integrate that between 0 and to the ln over 2 hour, and total all those up to get the total volume, and we're left with 3 litres. And that's paper 1 done.